Okay, any questions? Right now, Mike is the only one with an outline, as he just came into camera frame.
Oh. Had to be my appearance.
What was that?
Had to be my appearance.
Unfortunately, I couldn't hear all of it because, you know, I'm me. All right. We sort of give you the grand scheme of what's going on in terms of post-test 1A. This is sort of a process that I've developed over the years about how to approach a great number of problems. So the F stands for force diagram, which is what we're spending a lot of time on right now. Once you have the force diagram done, you then start, usually on these problems, you're trying to find acceleration or something related to the acceleration. So this is A for acceleration direction. Once you've established the direction which you expect an object to accelerate, you then set up the coordinate axes. So that sort of goes together. So you're establishing your, really don't care for the term, but I'll use it anyway, the X, Y axes, or your I hat, J hat axes, or whatever you happen to be using. Then you'll figure out what vectors you need to break up into components. So the decomposition. Because the decomposition depends upon how you set up the coordinate axes, which depends upon the direction of acceleration. Then you come up with the equations of motion. This is application of Newton's second law. Equations of motion is not directly related to chapters 2 and 3. Then there's the substitution. Because there are some formulas which are independent of the particular problem, such as weight is equal to mass times acceleration due to gravity. And then finally, solve. And I refer to this as the facades method. So I finished going through the sort of the regiment of the force diagrams, and then we'll actually take one of those and work through all the steps. And since we last left off with box on ground, let's now do the ever exciting box pulling box with rotor. I will label this 1, and this 2. Those are not masses, those are just identifying marks. So the first step of the force diagram, let's go ahead and establish a still Earth. I got object 1 there, got the rope, got object 2 here, and then the ground. All right, what force is acting on what, and in which direction?
Is there a gravitational force?
Is there a what?
Gravitational force.
I would hope so.
Yeah, so I think gravity is pulling on the object 2, which is pulling the rope, pulls box 1.
Okay, let's see if we can break down step by step though. Let's start out with the gravitational force. Which way is the gravitational force acting on box 1? On box 2?
Yeah.
On the ground?
Yeah.
Did you say down? Maybe?
Yes.
Yeah, remember that it's an attractive force between the small object and the planet. And so this is representing the planet. The force on it would be up. So weight 1, weight 1, weight 2, weight 2, and we assume ideal rope. All right, now what?
When you have tension,
I hope so. There's a rope there. So which way is tension acting? I guess it's the first one we had with tension. Well, we'll end up with 4 different vectors with tension. So where's the tension on this part of the rope right here? Which way is the tension acting? All right, well, I've seen fingers pointing in those directions, so we've at least identified it's horizontal.
To the left,
Why not to the right?
because it's being pulled that way.
And that's exactly the reasoning. So we have a marker graveyard down there. There's tension pulling the rope to the left. But forces come in pairs. What's the other part of that pair?
Towards down.
I've heard to the right and down. Okay, we've identified it's in some direction. The forces in the pair, what do we know about them? Skylar?
don't they face each other? Or,
Yeah, or they're either
or
directly apart or directly towards. So it would have to be to the right. What's pulling on the rope? Therefore, the other part of that pair, right there. If we were being picky about arrow length, those arrows should be the same size. All right. That end is taken care of. What about down here?
tension going down
Down on,
the rope,
okay,
and then going, is it going up from box 2? But then,
yep. On box 2. It's that tension up on box 2 which keeps box 2 from being in free fall. If that rope were cut, that box would just plummet. And so something's keeping it from doing that. It's that tension. All right, so this is fine. For an ideal rope, this is perfectly fine. Later on, when we do away with some of the ideal nature of it, then if we needed to put subscripts in here, which two would have the same subscript?
The FT that's on the horizontal, and then the FT that's on the box 1.
So those two would have the
Those
same?
two would have the same system.
What about these two?
Those two would also have the same system.
But different than those?
Different than those.
Okay. That is correct. So if on the complex force diagram, if you put subscripts here, 1, 1, 2, 2, I'm fine with that. Or consider it an ideal rope and just don't worry about the subscripts. If you're dealing with ideal ropes, you definitely need subscripts if there's more than one rope, but with a single rope, no. All right, so what have we done so far? We have done gravitational force and tension.
What is sorry, I didn't come in late, but what is the ball and line in between the rope?
This?
Yeah.
That's an ideal pulley.
Oh.
would there be friction on the pulley or just friction?
Frictionless is ideal.
So, would that be considered an O factor?
No, O is if I had thrown an additional force into it.
Oh.
That because when I separated it, I drew the pulley attached to the ground already, the pulleys can be considered part of the ground. All right, so we do have normal forces acting on what?
Box one.
Acting which way on box one?
Going up.
Yes, it is.
Down to the ground.
Let these blue markers work. All right, so I got a normal force there and acting down on the ground. Again, normal force is a repulsive force that keeps one object from going through another.
The other normal force would be the pulley, no? Because it is contacting the rope,
Okay,
so it would be away from the pulley and away from the,
so opposing each other?
yeah.
Which pair of normal forces should. So I've got one going in this direction. I don't know specifically the direction that it's going in. It's gonna be somewhere in this point of contact. It'll be somewhere pointing within this region right here. I didn't give you enough information to be more specific, so it's just some generic direction in that, like that. If you draw it straight up, I'll say, no, it's not straight up. If it's at a slight angle, give it a jaunty tilt. Y sub R, Y sub R,
Why are,
for rope. You do not have to go with the same subscript convention I'm using. But I tend to, when my subscripts, start from the top and work my way down. So since R is above the pulley, rope is above the pulley, I use R. Any other points of contact? Besides rope touching something, besides rope touching one or rope touching two, we've already taken care of that with tension.
no,
Probably the two biggest rookie mistakes I see here is some people will put a normal force up on two or to the right on two, but two is not touching the side or to this, so yeah, no normal force there. We are done with normal force. All right, other?
no. And I don't think there's any friction, even though we do, like, in this instance, the pulley is still. So, I mean, there might be a little bit of movement here, which could move the box a little bit. I mean, that's if we were experimenting, but theoretically, I don't think there's any friction. Because there's no desired movement.
If we set this up, nothing would want to move at all?
I mean,
If everything were frictionless,
right,
it would stay still? That's what you're claiming?
I mean, if box one and box two weight the same, but if box two weighs even a slight bit more than box one, then box one would move.
Whether box one moves to the right or not has nothing to do with the relative masses. Mass one could be a megagram, and mass two could be 1 gram, and there would still be movement, if the surfaces were frictionless.
Yeah.
There's friction between one and the ground, box one on the ground.
Which way is it acting on box one?
The acting this way, no, this way.
Is that your final answer?
I don't know.
Well, think about, let's go with sort of Abraham's thinking there that if box one does not move at all. Think about, I got 3 forces acting on it. If it is not going to move at, starts at rest and stays at rest, there has to be something that's gonna counter this force right here. So it would have to be that way. Which I think was your,
I think I'm.
the last answer.
Yeah, I got you.
And, yeah, why not? And where's the other, they come in pairs? Yeah,
Just under here.
and this is why, if it were frictionless, if that were gone, there's no way I can add up those three forces and have it add up to zero. Because if the forces add up to zero, it's in equilibrium, acceleration is zero, velocity won't change. So if it starts at rest, it would stay at rest if it's in equilibrium. But if I have just those three forces, I cannot add those three and end up with zero. I can go. And we're over. So that would be Y1 acting up, FT1 acting to the right, W1 acting down. There's a gap there. I cannot take three perpendicular vectors like that and add up to, I can't end up where I started. All right, we're done. Questions?
Was this the only one you've done so
Yeah.
far today?
Except for the one that's gonna be on the test, but you missed out.
I think everybody missed out.
Questions?
I'm still confused about why the friction's like this and not like this.
Friction opposes the desired relative motion. So let's say that you're David Blaine and you're underneath a plexiglass container here, and the box is sitting on top, right over top of you. If box one moves, which way is it gonna move? From your point of view. Friction says, no, I'm not gonna let you do that. I'm gonna try and stop you. So friction opposes that. So from the ground's point of view, the box is going that way, and therefore friction goes that way on the box.
So like the tension tugging it to the right, the friction drags it left.
Yeah, or tries to stop it going right. Now, you could make the argument that it's dragging to the left, but that makes it sound like if the tension disappeared, the box would suddenly start moving to the left.
Okay.
All right. And then a problem that you will grow to love and hate at the same time.
Box on the right.
That's right. Have I talked about the superpower? If I could get a superpower, what would it be? Because occasionally I get that question, and I had one student who would ask me, and whenever I'd come up with something, he'd already thought about it and all the problems with it, but it did come up with one that I don't think would have any problems. To control thunder. As in, box on ramp.
Oh.
It would emphasize
Sound effect.
things that I say. Yeah, the sound effect.
You just have a soundboard programmed into your everyday life.
I like, no, like he lived with this guy, clear day, he says something.
And if I made it loud enough, people would go, huh, Dr. Fox just said something.
I think we've already done this.
We did box on ramp?
We did box on ramp.
You can do the game.
How far, we will.
So we did box on ramp here. And then we did box swallowing, box on ramp, box on.
Yeah, okay.
Box on ramp.
Well, you know what then? If we've already done box on ramp, we're ready for an actual test level problem. So let's do a test level problem. This is all just warm up. And after the test level problem, we'll actually move to the next step. We will spend, obviously, we spend a great deal of time on this step. These will run through very quickly, but we'll do a whole bunch of these.
Smorgasbord, if you will.
If you will. It's supposed to be touching. Just let's not confuse this part of the stick figure.